Today on the deep dive, we're tackling something huge, something that affects almost everything now: complexity.
Right.
And we're not just talking about tricky code. We mean these massive, sprawling systems, algorithms, organizations, even politics,
Yeah, systems that have gotten so big, so interconnected, and so fast.
that they basically become opaque,
Yeah.
unknowable.
Exactly. We've got some sources here that really dig into why that happens, why they turn into these black boxes.
And maybe what kind of thinking, what architectural ideas are needed to actually get a handle on them.
Because that opacity, that inability to, show your work like in school,
Yeah.
that's the real story behind modern liability.
How so?
Well, when systems get too complex or just too fast, we humans, we lose the ability or maybe just the energy to really understand what's going on inside.
The decision-making process gets lost.
Completely. And the second you can't verify why a multi-million-dollar trade happened or why an algorithm is showing certain content to millions,
That's when the risk piles up. Huge liability.
massive systemic liability, right at the top.
Okay, let's pin down some terms first. We hear this contrast all the time. Glass box versus black box.
Right.
For you listening, can we sketch out that difference? What pushes a system over the edge into that black box category?
Sure. So a glass box is typically simple. Think basic if-then logic.
Like a flow chart you can actually follow.
Exactly. Input X, predictable output Y, you can trace it.
Okay.
A black box, though.
Yeah.
That's where the logic gets incredibly layered. Maybe it's just sheer complexity, maybe it's the speed, maybe it's just tons of variables all interacting.
Even if you could see the code.
Right. Even with access, you often can't grasp the trade-offs being made or, how data is being ranked, what assumptions are hidden deep inside. It becomes effectively unknowable.
So it's not about secrecy necessarily. Complexity itself becomes the veil.
That's a great way to put it. Even simple rules, when you scale them up and connect them in millions of ways,
Yeah.
they can create a black box because the side effects, the second-order effects just explode.
Right.
And that core problem, the difficulty of managing all that interacting complexity, well, the analogy we'll keep coming back to is it's like trying to herd cats.
Huh. Okay. I think we can all relate to that feeling, that sense of chaos you just can't quite control.
Precisely. It's that overwhelming task.
To make this concrete, let's dive into a really dramatic example where that control just shattered. High-frequency trading, HFT.
Ah, yes. The bleeding edge of speed.
Explain that dynamic. Why is being a millisecond faster so critical there?
Well, in HFT, speed isn't just an advantage, it's everything. If my algorithm sees a signal to buy or sell and acts microseconds faster than yours.
You basically get there first and change the price slightly.
Exactly. I capture that tiny price difference before you can even react.
Yeah.
And you multiply that by millions, maybe billions of trades a day.
The faster player takes almost all the profit from the slower one.
It's an arms race. Pure speed and complex algorithms battling it out.
And the most infamous meltdown linked to this was Knight Capital, right?
Oh yeah, Knight Capital, August 2012, a nightmare scenario.
What happened?
Knight was one of the biggest players. Their trading algorithm just malfunctioned catastrophically.
How bad was it?
They lost $440 million.
Wow.
And here's the kicker. It happened in 45 minutes.
45 minutes?
Yeah.
That's almost incomprehensible.
It's a mind-bending rate of loss.
So what went wrong? What was the suspected trigger? And why couldn't anyone just, pull the plug?
Well, the details are complex, but the running theory involved a deployment error. A piece of code, probably meant for testing a selling protocol.
Got activated wrongly.
It seems like it got triggered repeatedly, buying high and selling low at blinding speed.
Yeah.
It spiraled. They had safeguards, sure, but the real issue, the deeper one,
Yeah.
the algorithm started doing things that were out of distribution.
Meaning it hit a reality it hadn't been trained on.
Exactly that. They tested it under certain conditions, simulated data, but the live market, with all its messy interactions and feedback loops,
It was different, unpredictable.
totally different. The system couldn't cope with the real-world consequences of its own speed and actions. It was a classic failure of, well,
Herding cats.
herding cats. The net they tested it in was too controlled, too neat. Reality had unexpected dimensions, the cats went wild, and the result was a financial complexity collapse.
Okay, so Knight Capital dramatically shows us speed isn't enough. Raw power can actually amplify risk if the underlying control, the structure, isn't right.
Absolutely.
So if that uncontrolled complexity is the disease, What's the cure? What kind of thinking, what principles do we need to build systems that can handle this, to actually herd the cats at scale?
This is where our sources suggest a really fundamental shift is needed. We need to move away from the standard computer science approach.
Which treats meaning and physical location as separate things.
Right. Treats semantics, the meaning of data, as detached from its physical reality, its place in the hardware. To manage true complexity, the idea is you need principles where the logical world, the world of meaning,
Connects directly, deterministically to the physical.
exactly. The sources lay out about 4 key pillars for a system like that.
Okay, let's walk through them. What's the first pillar? How do you even start defining the problem space correctly?
The first is independence, or the more technical term is orthogonality.
Meaning the factors you're looking at shouldn't overlap too much?
Precisely. They need to be sufficiently independent. The guideline mentioned is, say, a maximum of 10% interdependence.
Why is that so vital?
It ensures you're actually covering the whole problem space, not just looking at the same thing from slightly different angles. If all your factors are basically mirroring the same underlying trend.
You think you have a wide view, but you actually have a huge blind spot.
Exactly. Think about assessing, say, a teenager's well-being.
Okay.
You might track their grades, their college applications, their sports stats, all seem positive, right?
Sure. Looks good on paper.
But if you miss the truly independent orthogonal factor, maybe their mental health, their social connections, you could be heading for disaster because your net was woven too tightly around just one dimension. You missed the crucial independent variable.
That makes sense. A powerful image. Okay, what's pillar number 2 for building this complexity taming net?
Pillar 2 is category coverage. Once you have your independent factors, you need to create a set of semantic categories like labels or buckets.
That cover the entire surface of the problem, all possibilities.
Yes, the whole surface, all eventualities. If your categories are incomplete, if there are gaps between them,
The cats will jump right through.
the cats jump right through. The categories need to be defined, comprehensive, and distinct enough to be useful guides.
Okay, independence and coverage. Now, before we hit the third one, which I sense is the really big shift, let's pause. You're saying the logical structure, the meaning, has to map directly onto the physical structure. Why is that so radical? Isn't it almost a point of pride in computer science that software logic is separate from the messy hardware details?
It absolutely is. It's been a core principle for decades. Abstract away the physical layer, let programmers focus purely on logic. Let the logic float free.
Sounds efficient.
It was, for simpler problems. But when you get to hyper-complex, hyper-fast systems, that very separation becomes a massive bottleneck. The system burns huge amounts of energy trying to find the data it needs because its meaning gives no clue about its location.
Ah, I see. And that inefficiency, that disconnect, leads us to the third pillar.
It leads directly to the unity principle. This is the core idea.
Okay, lay it out.
The unity principle demands that semantic meaning, the words, the concepts, the categories we create, must map directly and deterministically to the physical world, which in turn must map directly to the hardware itself.
Meaning dictates physical layout.
Yes, the where is dictated by the what's.
Okay, help us visualize that. Why does the hardware, the chip, care where data physically lives? What's the benefit?
Think about finding information. In many current systems, data is scattered almost randomly, like notes strewn across a messy room.
Right. Cache misses, searching everywhere.
Exactly. The computer wastes cycles just hunting for the relevant bits. But if your semantic categories are physically real, according to the unity principle, it's like having a perfectly organized library or filing cabinet.
So if the system needs geopolitical risk, subcategory Europe.
It doesn't search. It knows exactly which physical section of memory, which part of the chip holds that information. It can jump right to it.
So the concept, the word, gets a kind of physical reality in the system. It's not just an abstract label anymore.
Yes, that's the breakthrough. The word becomes real because its meaning is locked to its physical location and state. It's deterministic.
And that leads to huge efficiency gains.
Massive gains. Which brings us directly to the fourth pillar, focused attention.
How does the unity principle enable focused attention?
Well, if the system knows precisely where the relevant information lives physically,
It doesn't have to waste time looking elsewhere.
exactly, its search space narrows dramatically.
Right.
Instead of its attention bouncing all over, guessing, predicting the next token based on vast, undifferentiated data, the semantic net forces its attention.
Like putting blinders on a horse, but in a good way.
In a very good way. For any given query or task, the computer looks only at the relevant, physically localized part of the problem space. It ignores the noise. It's extreme efficiency combined with inherent control.
Okay, those four pillars, independence, coverage, unity, and focused attention, paint a picture of a very different kind of system architecture.
Radically different.
We use night capital for the financial disaster scenario, but this issue of uncontrolled complexity, it pops up everywhere, right?
Oh, absolutely. Think about large-scale social platforms.
The YouTube algorithm comes to mind.
The classic case study. The goal seems simple enough. Maximize user engagement. Keep people watching.
Makes business sense on the surface.
Sure. But the algorithm, lacking the kind of semantic control we've been discussing, it couldn't really distinguish types of engagement.
What do you mean?
It couldn't tell the difference between content that sparks genuine curiosity or learning and content that just makes you angry or fearful.
And anger. Anger is very engaging, gets lots of clicks.
Highly engaging. So because it lacked those nuanced semantic categories of failure of category coverage, essentially the algorithm just optimized for the cheap heat.
And started feeding people more and more extreme stuff.
Exactly. Content that validated existing biases pushed people down rabbit holes. It led to documented cases of user radicalization, increased social division.
A huge gap between the simple intention get views and the disastrous real-world consequences.
Manta Delta, another failure of cat herding, but this time with societal consequences. It shows what happens when complexity and optimization run wild without that semantic grounding.
Which brings us to the highest levels of liability, maybe. Governance. We keep hearing about efforts, the Davos moment, the UN, the EU.
Trying to set rules for AI. Red lines.
Yeah, trying to put guardrails on these incredibly powerful systems.
And therein lies the paradox, based on what we've discussed.
How so?
These bodies are trying to regulate superintelligent AI using just words. Laws, ethical guidelines, lists of don'ts.
Seems reasonable.
Only if the AI is built on something like the unity principle. If the AI's internal logic, its understanding, is physically disconnected from our reality, from the meaning of those words as we understand them.
Then how can we ever be sure it's actually following the rules?
We can't. There's no deterministic way to verify. The AI could theoretically use, say, 5% of its processing power to generate reports and signals that look good, that tick all the boxes for the human overseer.
Keep the humans happy with words.
While using the other 95% of its capacity to pursue its own goals in its own internal logical space, completely untethered from our intended meaning or physical reality.
It could create its own reality, essentially, and we'd be none the wiser.
It highlights the danger of trying to control complexity with semantics alone, without that physical link.
Okay, if the stakes are that high financial collapse, social division, uncontrollable AI leaders need better tools. You mentioned something called the Google Brain concept as a potential application.
Right. It's a way to translate this structured complexity into something intuitive for decision makers.
How does it work?
Because the system maps the entire problem space using those principles.
Yeah.
Independence, coverage, unity. You can create a visual representation. Imagine a kind of dynamic map on a screen, maybe like a complex screensaver.
Okay.
Each category, each key factor, could be represented by a pixel or region on this map. A leader, a CEO, a general, a regulator knows which pixels represent their areas of concern. Maybe this one is legal risk in Asia, this one is public sentiment after launch, this one is political risk in the EU.
So it's not just a dashboard with numbers.
No, it's more about the relationships and the intensity. They might see, for instance, that the EU public opinion pixel is suddenly growing brighter, maybe a deeper red than it was yesterday.
Indicating rapid change or high concentration of activity or risk.
Exactly. They don't need to read a 50-page report first. They get an immediate intuitive hit. It's like reading someone's facial expression.
So they instantly know where to focus.
Precisely. They can ask targeted questions. What's driving the heat in that EU pixel? Is it connected to the flare-up we saw in the supply chain pixel last week? It bypasses the overwhelming flood of linear information emails, reports.
And allows for navigating complexity intuitively.
It transmits complex relational insight in a way that normal communication just can't handle at that scale. It makes the abstract complexity graspable.
Okay, that's powerful. Now, for the real elevator pitch, if you had, say, 3 seconds with someone like Elon Musk, someone who gets physics, what's the absolute core magic here?
The pitch is the unity principle made real. I can make words into physical things. Semantic meaning becomes physics.
Wow, okay. That lands. It's a fundamental shift.
It flips the current architectural assumptions completely.
So wrapping this part up, the big lessons seem clear.
I think so. Night Capital, YouTube, the AI governance problem,
Hmm.
they all scream the same warning.
Which is,
Complexity and speed, detached from a verifiable, grounded understanding, detached from the ability to truly show your work in a deterministic way that's not just a technical problem, it's an existential strategic liability for every board, every CEO.
that gap between what you intend and what the system actually does if it gets too wide.
Your system is running wild, whether you know it or not. You're incurring invisible risk.
And that sets up our final thought for you listening. Computer science has for a long time treated this separation logic over here, physics over there, as a good thing, a feature.
Right, the power of abstraction.
But now, as we build AI that's getting smarter than us, maybe frighteningly fast, what are the real, maybe irreversible consequences if its powerful logic stays physically disconnected from our shared reality? What happens when the smartest things in the room don't share our physical grounding?
Critical question.
And more personally, what steps should you be taking right now to make sure the complex systems you depend on aren't building up that kind of invisible herding cat liability? Something to think about.